Hey everyone, so today I'm going to be teaching pre-order, in-order, and post-order traversals. These are variants of depth first search, but they're really important because depending on the problem, using the right traversal here will make your life a lot easier when solving the problem. And some problems could really be only solved using one of these variants. Maybe you can make it work for some other problems, but yeah, I'm going to show you different examples where if you choose the right traversal, you have a really elegant algorithm. So, what is pre-order, in-order, and post-order traversal? Well, it's pretty much what it pretty much means is it's the different ways that we can visit a node when we're doing a traversal. So we can visit the node first before we visit its left and right children, or pretty much like operate on the node first before we go to its left and right children. That's why it's called pre-order. We can visit the node in between the left and right children. So we go down to we traverse to the left first. Once we're finished with the left side, then we visit the current node, and then we finally go to the right. So that's why it's in order. And then post order is we visit the node last. So we get the results from our left and right children first, and then we visit our node. Right? Like the way I like to think about it is it when I'm looking at a problem, I like to think what sort of information do I need from my left and right children? If I don't really care about my left and right children, or maybe I have to generate some value and then pass it down to my left and right children, then I'm going to do a pre-order traversal. Right? If I need to be passing anything down, or I don't care about, I don't care about the result from my left and right children. If I care about the result of my left child before I'm looking at my current node, then I need to do an in-order traversal. And in some algorithms, I want to know what happened in my left and right children, and then make a decision on my node. And I have examples for that. That's gonna make a lot more sense. So just keep watching. So yeah, let me quickly draw out. Let's go through what the pre-order, in-order, post-order, how it would actually fill out these arrays. And I would do this as an exercise for yourself, because even when I was first starting, I did this exercise. So pretend we have node left. Put this here. So I also have a video on how the recursive call stack works. So if you watch that, you'll be able to understand this part when I do this. But this is how a pre-order traversal works. Pre-order means we visit the node first, then we visit the left, then we visit the right. Right. So what's that gonna look like? First, we're gonna visit the node. So we go here. So we visit the node there. And by visit the node, then we append that to the list here. We visit one. Then we visit left. When we visit left, we recurse down this way. Then we're at the left, right? We don't execute right until the left subtree finishes. Because we call our recursive function on left. We put node here, node 2. That goes into our pre-order here. And then now we go left again. Now when we get to left here, we put 4 in. We visit that node. Then we visit the left, that's none. The right, that's none. These are null, so we don't recurse those. Now we finally go back up, and now we hit the right. So we go here. As soon as we get here, we process the node. So we put 5. That removes here. Left and right don't go. So now we recurse up, and now we get all the way. There's no more operations to do here, and now we come up here, and then now we're gonna go right. We can see 3. Right. So you can see how it goes. It's a pre-order. When we recurse, we process it right away. So this would hit 3. Then we hit node again here. Then we go to the left. Get 6 here. Left, right. We go back up. We hit right, then we go here. Now we put node 7 right here. Yeah, like this. And then we have the left and right. So this is what the pre-order traversal would look like. Let's copy that. Let's see. Yeah, that's what the pre-order traversal would look like. Now let me just quickly delete this. You could delete that. Or no, keep that around because we're gonna do it for the next one. What should I do here? Okay, wait. Let me clean up this tree. Yeah, so that's what this is what a pre-order will generate here. 1, 2, 3, 4. So it'll go like this. It'll go 1, 2, 4, 5, 3, 6, and then 7. It visits the node as soon as it gets to it in the recursive call. Now let's visualize what an in-order traversal is. Let me set up the tree again. So with a in-order traversal, this is how it's going to look like. When it hits this node, it won't actually visit this node first. It's going to go to the left. When it hits this node, it's not going to actually visit this node first. It's going to go to its left. This one is going to go to its left and see that, and then see it's none and come back up. Now finally, let's just go like this. Now finally we add 4 here. Because it has left to exhaust, or it doesn't have a left to exhaust. It comes back up. Now we visit the node 4. Then we visit the right, that's none. Then we go up here. Now we go back up because this subtree is exhausted. We go up. Now we finally process 2. And then go right. We go right. We don't process this node, right? That's a pre-order. We look to our left, that's none. Then we process 5. We process 5. We go right and nothing's there. And then finally we recurse all the way up. We get to 1. 1 here is, yeah, we already exhausted our left subtree. Now we finally process 1 here. 1. And then we go right. Go right. When we get here, we don't process this node. We look to our left first. So we go left, go down this way. This one looks at its left, it's none. Then we finally do 6. We look at our right, it's none. Then that's crossed out. Then we go back up again. And then now we finally put 3. And we go, and then we go to our right. Once we go to our right, we look at the left, it's not there. Then we look at the node. So that's kind of how it would work recursively. Then you finally go up and you return. So you see that it's putting the nodes in a different order. It's going, because it has to go all the way left. Then we go 4, 2, then it goes right. Then it tries to go all the way left, but there's nothing. Then it goes 5, then goes up, finally goes 1. It pretty much diverts or withholds the operation until the left side is finished, and you'll see why that's useful later. That's what an in-order traversal is. Let me show you what a post-order traversal looks like. Let me just quickly clean up this graph again. Okay, let's get into the last one, which is a post-order traversal. So in the post-order traversal, we visit our left and right before we ever visit our node. That means by the time we ever visit this node, we would have already visited all of these other nodes. Or by the time we process this node. So how does that look like? Let's start here. When we call the recursive function on here, instead of processing this node, we automatically just call into our left child right here, and then we go down here. Then when we get to this node right here, we do the same thing. Instead of processing this node, we automatically just call into our left child right here. Then we get to this final node. We look at the left and right, and there's nothing there. Now we finally process this node. So we process 4 right away. Now we go back up here and we look into the right child. Right child, left is none, right is none, so we visit the node. So we get 5 here. Then when we recurse up, we finally visit this node 2 right here. And then we recurse up, and then now we completely visited our left subtree. Now we go visit our right subtree. Go down here. We go to our right subtree, cross this out. Instead of visiting node, we go left. We go down here. Left and right are none, so we process the node. 6. We come back up here to 3. We automatically go into our right again. Now we go down to 7. 7, left and right is none. So we process the node at 7. And then finally we process 3. And then finally, we get here and put 1. You see, by the time we get to the node, we would have processed left and right children. So this is usually useful for problems where we need to know when we need to know information about our children when we're making a decision at this node. So for example, this is the maximum depth of a binary tree. We need to return the maximum depth of numbers of nodes along the longest path from my root to a leaf. So pretty much when I'm processing this node, I know I'm the root, right? If I just know what's the longest path what's the longest path from my left child and the longest path from my right child, I just need to return the maximum of those two values. But I would have need to have recursed fully on the left and right subtree in order to know that. That's why post-order traversal will work in that case. So yeah, it would lead to a graph or we would have visited the nodes in these order: 4, 5, 2, and 6, 7, 3, and 1. You can see kind of like visiting them from the bottom up there. So yeah, like if you want to delete nodes in a graph, that's also one edge or one use case. But yeah, that's what a pre-order, in-order, and post-order traversal is. I'll explain it more. Yeah, these are way easier to do recursively. There's problems called there's a series called on LeetCode where you have to implement pre-order, in-order, and post-order, and it's pretty easy recursively, but they also tell you to do it iteratively, and it makes it way harder. And yeah, let me just get into the examples now. So this is the first example that I want to go through. We have the question is 404, sum of left leaves. We need to figure out the sum of all the left leaves. So pretty much find all the leaves that are left leaves and add them all up and then return that result. So a leaf node is a node with no children. A left leaf is a leaf that is the left child of another node. So yeah. The way I'm going to solve this is with a pre-order traversal. What I'm going to do is for every single node, because I don't really care what order I visit or what order I visit them. or in this case, I might as well just visit, like every time I get to a node, check if it's a left leaf. If it is, we return true. For every node, check if it's a left leaf. If it is, add to some global result. So yeah, I just want to do that every node. I don't need to care about the result from my left subtree. I don't need to care about any result from my right subtree. I could just do it as I see the nodes. So that's why that's why I made the decision to do a pre-order. And pre-order is basically just a regular DFS. So what we're gonna do is, let's just write the pre-order function here. And we'll also write we're gonna store a init function. Init function, we're gonna have a init function so we can store result, which is our global result here, the variable that we're gonna update when we return. And we're gonna do we're gonna do a pre-order traversal on the root. And then finally, we're going to return self.result right at the end. And yeah, we're going to need to keep track of a couple things here. I mean, first off, we're keeping track of the result, and we're going to return that. Result is a total sum. But what we'll need to do is we're going to pass in a flag called is left, right? Because when we get to a node, we need to know that if it's a left child. So sort of the parent has to tell us that, because the parent knows if it's the left child or not. And it'll tell this child it's its left child, and the other child is this right child. So we can just say this is left. Initialize that to false. When we're at the root is not a left child of anybody. So I'm pretty sure this is false. So we initialize is left to false for the root. But what we do is, if the node is none, just return. We don't want to process a node that's null. We don't want to get into a null pointer exception. But what we're going to do is we will just check the node right away. So if is left, and we're gonna pass in the node here. And node.left is none, and node.right is none. We add this to the result plus equals node.value. So we could see we process it, we process the node there, and then we recurse our left and right. Self dot pre-order, we pass node.left. It is the left child, so we return true there. And then for our right child, we put false because it's not a left child. And then we return here. So I think something like that should work. And yeah, we're saying this is a pre-order traversal because we process the node here, then we go left, then we go right. And this is boilerplate code that I do for a lot of DFS functions, but I hope that made sense, and we're gonna move on to the next variant now. So this is the second question. We need to return the minimum absolute difference in the binary search tree. So we're given a binary search tree, and we need to return the minimum absolute difference between any values in the tree. So yeah, how do we do that? Well, one thing is we could just perform a DFS, get all the nodes in the tree, pretend we get 1, 2, 3, 4, 6, and then sort them, and then Once we get them in sorted order, 1, 2, 3, 4, 6. Once we get them in sorted order, we just need to compare every adjacent element and see what the difference between those two values are and calculate the minimum one. So the answer here is 1. So yeah, that's one way to do it. But you could actually just do this in one pass if we do an in-order traversal. From the fact that this is a binary search tree, we need to, well, most interviews, they're going to want you to do it this way. But we have a binary search tree, right? What's a binary search tree? It means it has this property. All nodes in the left, are these unique values, the number of nodes? All nodes in the left subtree are smaller than current node. All nodes in the right subtree are greater than. Let's just assume that it's exclusive right now, and you could format this property to be inclusive of, it could be like smaller or equal to, but we want to simplify this. Let's say all the nodes in the left subtree are smaller than the current node, and then all the nodes in the right subtree are greater than the current node, and apply that definition recursively. So what does that mean? If pretty much, yeah, since we have a binary search tree, it holds this property. And I'm going to state this one thing right now, that if you do, I already wrote this down right here, in order traversals, in binary search trees, in order traversals visit nodes in sorted order. So if you do an in order traversal on a binary search tree, if you do an in order traversal on binary search tree, it visits all the nodes in ascending order. So we'll get the nodes in 1, 2. We'll get, if we have a binary search tree here, we'll get the nodes in 1, 2, 3, 4, and 6. And that's a key thing that you need to know. Kind of just memorize that and make sure. But it all makes sense when you look at the binary search property. Because what's a in order traversal? It's you visit the left, then you visit the node, then you visit the right. If I visit all of my left nodes before me, and all my left nodes are smaller than me, when I get to my node, when I add my node to the array, I would have already added all of the smaller elements first, then I add myself, then I'll start adding the elements that are greater than me. So if we just do that, it'll print the array in sorted order. So pretty much how I'm going to solve this problem is I'm going to do an in order traversal, and I'm just going to keep track of, I'm going to do an in order traversal, and I'm just going to keep track of the last element that I've seen. Yeah, I'm going to, because we know that's going to input it in sorted order, pretty much I'm just going to keep track of the last element that I've seen and compare that with the current node I'm visiting. So it will essentially keep like the last element, and then we'll visit. We know we're visiting nodes in sorted order. So I'll just compare my node with the last one that I saw, and then calculate that difference and minimize that. And then yeah, when we visit another node, I just look backwards. So I'll show you how that code looks. Let's define the same thing, like a init function. Hopefully that made sense. Try this function out and reason about it for yourself. Why this works easy with an in order traversal. Let's say the result, we're trying to minimize some value. So we'll initialize this as like some super high value. And then we'll do our left node. So what we're going to do is we're going to do an in order traversal. Self node. If node is none, this is just the base case, so we could return. But what's an in order traversal? First, we're gonna look into our left, then we're gonna look into our right. So we're gonna do cell dot in order self dot or node dot left. So we're gonna do left. Then we're gonna process the node. Then we're gonna go right. So do something like this. Right. So what do we do when we process the node? What we're gonna do is when we process a node, we're gonna say if self.left, if there was something to our left, because we want to handle this case, and then once we handle the first node we visit, there will always be a left child. There will always be let's say last left. There will always be a last left. Or let's say we'll just say last. This is the last node we seen, because we know that when we're going in order, the last node that we seen is the value that's the largest value smaller than the current value we're looking at. So if that element exists, we're gonna have to update our result. So we'll do self.result equals the minimum of the current node dot value minus self dot last dot value. So this is the difference between the two nodes. So we'll take the minimum of the current result and that, and then we'll do self. What we'll always do is after we visit a node, we're gonna store it. So self.last equals the current node. So we visit left 2, then we visit 3. We know our last one was this one. So yeah, so you can see that this is once we visit it, we add it to our last, and then we would just return here, and then we just do self return. Finally, we just do return self dot result, and then we'll call self dot in order on our root. Hopefully that should work. But yeah, we used all the properties of the BST and implemented in order traversal. You can see it's in order because we go left, we recurse left first, then we go into the node, and then finally we go to our right. So hopefully that makes sense. Let's move on to the next example. So this is the last question I want to work through, and I already hinted at it at the start, where we're going to be doing a post-order traversal. And the reason is, let's just walk through a question. We want to get the maximum depth in a binary tree. So we're pretty much given the root of a binary tree. We need to return the maximum depth. The depth is the number of nodes along the longest path from the root down to a leaf node. So what's the longest path here? It's 3, because there's 3 nodes on the road to that path, or on the like pretty much on the path to that leaf. So how are we gonna solve this? Well, pretty much pretend we have. Let's just graph this out a little bit. Pretend we have 1, 2, 3, 4, 5. This. Pretend we have a tree like this. We want to know what the longest path is between this node and any of the leaves. So let's see here. Or we need to know how many the longest path here. Pretend that we knew that in our left subtree the longest path was 2. And this was the value returned. And we know from the right subtree, the longest path we know is 1, 2, 3, 4. Then we know if we just add ourselves to the path and take the maximum of those, the longest path would be 5. Right? But we would only know that after our left and right sort of returned. But okay, let's go on this side. How would we know the longest path to get to this node? Well, what if we knew that our left, the longest path is 1, and from our right, the longest path is 3? Then we just need to add ourselves to that node when we return up. We just need to find the maximum of our left subtree and our right subtree, the maximum path of our left subtree and our right subtree, and add ourselves to it. So if we kind of do that for every single one, you see how this one would return 4 up. And then what we do here. Yeah, if we pretty much... Okay, what do we have here? Right. Our left subtree returns 0. Our right subtree would return 2. But yeah, since it's a post order, it would kind of play out like this. Let's just assume this is 1. Post order means we do left, right, and node. So when we go here, we automatically go to our left. Our left and right, we process our left here, and that will return a 0. And then we process our right, that will return a 0. And now what's the longest path that I can get here? Well, it's 0. And then but if I add myself, it equals 1. And we kind of return that up here. So that's how we get 1 here. And since this is a post order, we don't process this node yet. We go down to our right. Then we go down. We don't process this. We go to our left here. This one returns 0 and 0. And then returns 1 back up here. Now we have our left. We recurse again. This one returns 0. Then we go to our right. We go to our right here. The right here goes to its left, and we go 0, 0. This will return 1 because we add ourselves to the max there. It looks to the right. It returns 0 here because there's nothing in the right. And now, what's the max path we can get? Well, we know the max path is 1 to our left. So if we attach ourselves to the left path, we add 1 to it, so we get 2 here. Now we have two options. We either attach ourselves to the left path or the right path. We'll attach ourselves to the right path. That gets us 3. Sorry, 0. This returns up 1. So this returns up 2. Oh yeah, so we get 3 here. Now we have option of 3 and 4 because now we're finally processing each of the nodes. It's like a post order. Now we're finally processing each of the nodes. We're gonna want to attach to ourselves our longest one, which is 3. So we're gonna pass up +1 there, and then we get 4. And then you can see finally at the end, we process our left and right, and now we have our decision. Should we attach ourselves to our right child or our left child? We're gonna attach ourselves to the longest path in the right, and that should equal a result of 5. That's why we do a post order, because we want to know the results of our left and right before we do anything with the current node. So how do we actually implement that? So how we can do that is if the root, what we can do is we can create a post order function. And then we always have a base case. Let me remove this. If the node is none, just return 0, because there's the longest path there is actually 0. There's no nodes. And then what is a post order? Left, right, and then you finally visit the node. So how that's gonna look is we're gonna do left result equals self dot post order of node dot left, and then we'll do the same thing for our right. And then now that we have the result from our left and right, we could finally generate the result here. So we'll add ourselves to the longest path. So we'll say best path is equal to the max of either the left result and the right result. Now if I add myself to the best path, yeah, if I add myself to the best path, then I maximize that. I maximize like the depth there. So we can just do return self dot post order under root. Run that. Beats 100. And yeah, you could see this is a post order because we visit our left, we visit our right, and then finally we visit our node. So hopefully that made sense, and now hopefully that you clearly understand the difference between the different variants here and why it's actually important and why people even teach those. But yeah, that's pretty much it. I think some common pitfalls would probably be like forgetting the order of operations if you're doing it. So yeah, like understand the different traversals and use the right one. Yeah, you could confuse the left and right subtrees. You could a lot of the edge cases are usually with the handling the base cases, honestly. So how do you handle null nodes if and how do you handle when to recurse or not? Um, yeah, cool. I think that's pretty much it. You don't really need to handle anything. Sorry, I keep blocking it. You don't really need to handle anything related to scene arrays or loops or anything like that because it's usually these are for trees. But you could actually run this on a graph too. That's one thing. So yeah, I think that's everything you sort of need to know about these variants. So yeah, see you in the next video.